Hello and welcome everybody to a new video. So this is part 2 of my series where I'm messing around with the FAT32 file system. So you may remember if you watched my previous video, there's a link in the description. The last time I kind of did a bit of a rundown on how the FAT32 file system works and explained a little bit about why I'm doing this. Quick recap, this was originally just meant to be a bit of a side quest mission for another project I'm doing where I'm trying to write to an SD card just to log some data out of an embedded systems project that I'm working on. So basically, I got to the point where I was able to write raw data to an SD card. But that wasn't much use to me because I couldn't then read that raw data in a nice way on my computer. So that led me down this path where I needed a compatible low-level FAT32 driver system that I could run on my embedded system chip. There are existing ones that do this, but I decided, foolishly I suppose, that I wanted to do it myself. I also had a very specific requirement in that the SDIO package that I'm using to communicate directly with the chip at the low level has this requirement that it has to read and write strictly in 512 byte chunks with a logical block address that it uses from there. So that's a little bit of a constraint that isn't necessarily there in all the libraries that exist to do this stuff. So I decided I was going to build my own one from scratch using that constraint kind of baked into the core concept of how it works. And I thought it'd be a good learning opportunity for me to get going. So the last time we left this, I had written, so the original, the actual final product of this, I'm going to write a no SCD Rust library that I'm going to then be able to run on my embedded system, which is all running Rust. But for prototyping purposes, I decided I was going to prototype this whole thing in Python, which is the code that we're looking at today. So this is my GitHub, carry3 /FAT32 pi, FAT32py. So this is my prototype that is written in Python. So I chose Python to do my prototyping just because it's kind of quick and easy, and it means that I'm not sort of constrained by some of the things that I will be constrained with when I go to implement this with Rust, but I can think through the actual problem solving itself rather than being worried about the language constructs that I'm going to have to kind of grapple with a bit, because I'm going to be doing some sort of new conceptual stuff in Rust that I haven't done before. Anyway, that's kind of an aside. So this is my Python code. So if you go back, a couple of weeks in the history of this, all I had was just being able to read from the disk. I couldn't write to the disk, and that was where we left the last video. Was my next step was to figure out how to write to the disk. So it's a couple of weeks later, and I've managed to be able to write to the disk. And I've done a good bit of other changes in here, which I'll talk about as well, because some of them are kind of cool. So first thing you may notice up here in the README, you see this little test run, which says passing, which is very good. So I added tests, and they're just running with a GitHub action. So you can see here, go down, see the run tests, and yeah, this shows me the output of the tests. So they passed in like 90 seconds to run the tests. That's not very fast, but there's a reason why. I'll show you in a second. So yeah, that's nice. But the reason why I wrote tests was like, this is only a personal project and this is somewhat throwaway code. But while I was working on the actual write logic, I realized that I was kind of struggling with doing some of the very basic stuff, and I was kind of getting myself into knots, and I had no way of testing the code as I was writing it, which is quite frustrating. If you're a developer, like a full-time developer, you'll know this kind of process called TDD, or test-driven development, where the idea is that you come up with the tests that would assert that your program is working. You write the tests first, and then you write the code, and you know you're finished when the tests all pass, basically. So that's sort of a framework you can use for development. Some people use it, some people don't. I do it at times, but for this, it became quite a handy thing to have. It's like, well, okay, if I'm writing to a disk, I could very easily just tie myself in knots if I'm writing to a physical disk, because I could wreck the disk just by writing to it and overwriting data in a bad way, and then the disk is permanently in a bad state. And then I don't know what I'm supposed to be doing as I'm testing it. So for reading, this is obviously not a problem, because all I'm ever doing is fetching data from the disk, so there's no chance of that happening. But if I'm testing writing, I need a repeatable setup so that I can actually reliably test what's going on. So for that, I decided to implement this thing in my tests, which is kind of cool. So if we go to my conf test down here, I set up basically a fixture, which you can inject into every test, and it gives you an instance of my disk object, which is what's used to access the disk, all spun up a brand new one for every test run. But most importantly is it does it with this in-memory temporary disk that I created. So you see here, there's this test image. So what I did was, from scratch, I created an image on my computer. I formatted it to FAT32, I mounted it, I threw a couple of files into it, and then saved it basically. And so I have this this drive here. So if I go back up to test into data, yeah, I've got this .image folder, which .image file, and this is just a FAT32 drive. It's 64 megabytes of data. That's it, and it's an allocated FAT32 disk that has some data stored in it. So if I load this, basically access it as a file, which is the same way, if you remember from our last video, the same way all we do to access the FAT32 disk at a low level is just open it as a file and just read the bytes and write bytes to it. So if I do that with this disk image, I have this reliable starting point every single time that I want to do something, so I can test, and I don't have to worry about overwriting stuff or wrecking anything. I always start with a clean slate. So in my conf test, the way I do that is we basically make a temporary file copy of the disk image. We attach it to the disk instance. We yield this out to the test. The test does whatever it does to it. And then at the very end, once it's finished, it just deletes that file, the one that we modified. And we get a new disk each time, which makes this really, really easy to test on and really, really easy to iterate through, because I don't have to worry. I have a clean slate every time. And it also means that the tests that I write always have the same data that they're working on all the time. So it's really nice. I left instructions in the README down here at the bottom for how you can create your own disk image. So if you're messing around with this and you want to create a different disk image with different files on it, or you want to create a bigger one or a smaller one, or experiment with different stuff, you can use these commands here if you're on Mac at the very least, to create your own disk image and mount it to your system and do what you want with it then. Yeah. Is there anything else different? So that's kind of it really in terms of the structure of everything that I changed, and just some nice stuff. I updated the README with a few things. I added a few more pieces of example code, which I can run now in a second, and you'll see them. Yeah, that's about it really. So let's maybe have a look at some code and run some stuff. So as before, we can do UV, and then we can do run, and then we can run most of our stuff. So the first thing I can run is I can run PyTest, which will just run all the tests. If I do .vv, we'll get a verbose output. .s then gives me, it shows you what, if your code prints anything, this will render it out to the screen. This also, one of my tests that I wrote, which I can show you here, these are shown in the File Explorer, is for testing that my examples run. So I have this examples directory up here with some files in it. So this basically is just a test harness that just executes each example so that you can see that it actually works. The examples are baked in so that they use that same image, and then also news up a temp one, and then we'll delete it afterwards. So that's all wired in, which is quite nice. You can also pass in your own file path, which I'll show in a second, which is nice, so that you can test it with your own physical disk if you want using these things. But yeah, for now, let's just run the tests. So hit the button, and this is running the examples now. So it'll start to just blot out a bunch of stuff onto the screen. So this is just the outputs of all of those examples. This is just a big lorem ipsum, and then this is just what those examples do. So this is one here that takes a file that exists and appends to it. Here's one that creates a new file with nothing in it and then adds data to it. And then this is just the one that just reads all the files that are on the drive and spits them out. So I remember just a minute ago there, I said that the test suite that I have is taking about 90 seconds to run, which is quite a long time. And you'll notice that there's a bunch of these tests here that have already passed. So they've already run. but you've got this one at the end, which is just still sitting here executing. So this is a special one that I added at the very end. So they do various things, like just creating, appending, creating, like testing what happens if you try and write a lot of data to the file or to the disk. And then this last one just keeps writing data. There we go, just finished, until it fills the disk, basically. So the disk can no longer allocate any memory. And so that just has to sit there forever or for ages, trying to write to the disk, write to the disk, write to the disk. But you notice how slow that was. That kind of shows you how writing to this disk with this code is not super efficient. So obviously this is running Python, not the most efficient language. I would expect when I run this in Rust, it'll be a bit more efficient. But at the same time, the algorithms and the way I have to do this with the 512 bytes at a time, reading and writing, is not super efficient. So I will need to probably tweak my implementation a bit and see, but I don't expect that this is going to ever be a very, very efficient way of reading and writing to the file. But it's kind of a needs must with the low level constraints that I will have with my 512 blocks at a time reading and writing stuff. So yeah, kind of is what it is. But this is cool. The test, if I can enter my test, it's the very last test here, and it's really simple. Just starts writing to the disk, and then it uses this PyTest raises, so it expects that it will raise an exception for disk full, which is one of my custom exceptions I've written, and it does. It just takes 60 seconds on my local machine to run. In the GitHub action, it takes about 82 seconds, I think, so it takes about 20 seconds longer to run. Anything else interesting that I did for testing stuff? Oh yeah, one thing I did do. So I added to the disk itself. Where's my code? FAT32 disk. Also, sorry, I should say I kind of redid the modules here and split some stuff out. So I was originally just had this one file, which is one module that had everything in it, and it is already, now it's done with documentation, etc. It's 650 lines of code, which is quite a lot, and that's been split out. So I split some of this logic out to these models. So I created models for the BIOS parameter block and for the partition and for files, and gave some of the functionality back to those models themselves. So this is like more than 1,000 lines of code for everything. Basically, all of the code is in these two files. Still 1,000 lines of code. Now there's a lot of documentation written, so you know that takes up a good bit of space, but still it's a non-insignificant amount of code written. But in here anyway, what I was saying was I added a property to the disk, which is up here, reads and writes, and these hook in directly to the read and write methods, which are, where are they defined? They're defined here, yeah. So we basically have this +1 operation every time we read and every time we write to the disk. And then what I've been able to do is I zero them out before each. So these are the main methods on the disk. You've got the init method, you've got list root files, you've got read file, and then append to file, create file. So these I zero these out before each top level method is called. And then after it's returned, you can assert, which I do in tests, on how many reads and how many writes they have. So the reason I did this is because I was thinking along the lines of, well, so yeah, here we go. So we say if we create a new file, this is going to do 6 reads and 2 writes to the disk to create a new file. So the idea with this was that I could experiment with, well, if I make tweaks to the algorithms here and here, can I reduce the numbers of reads and writes that are required to get the same results? I haven't messed with that yet. I haven't attempted to do that yet. I might not do that in this version of it, in the Python version. I may try and do that in the Rust version if I find that it is untenably slow to work with in practice. But if it's not, then yeah, I won't bother. The only real reason to do that would be if I'm using it in my embedded system and I'm finding that just reading and writing to the disk is killing the little tiny embedded system's performance to an absolute crawl, then I might. But if it isn't, especially for just like appending to files, because that's mostly what it will be doing, then I probably won't. I'll probably leave it, but we'll see. So where does that leave us then? So we talked about our tests a little bit, our setup here. I suppose maybe I'll talk a little bit about the overall like writing logic that had to happen. So writing is a is a good bit more complicated than reading. There's quite a lot going on. So the way I actually started with this was I was going to start with creating a file as being the first thing I did, but it's actually a bit more complicated than just appending to an existing file. So I decided to go with appending to a file. So if we just take a step back and just talk about what it means to append to a file when you're in your FAT32 system. So we know from previous video, you have your FAT records, which, you know, they're sequential records that are a linked list that tell you where in the data segment of the disk your data is that actually represents the file itself that you want. So if you want to write some data to the end of that, what you have to do is you have to walk the clusters in the FAT entry. You have to find the last cluster. You then have to go to that cluster on your disk. You have to read the cluster until basically the end of the data that's in that cluster, and then you have to insert bytes onto the end of that, and then that's it. That's you writing to the disk. So there's a lot of different cases you have to cater for. The simple cases where the data you have, say your cluster might have 10 available blocks left on the end of it. You want to write 2 blocks to that. So therefore you find the point where the data ends, you add 2 more to it, done. That's it, you return, you're finished. It's more complicated where, say, if for example the cluster you're in only has, say it has the same 10 blocks left, but you need to write 15 blocks to it. What you then have to do is you have to write 10, realize you've hit the end of the cluster. You have to go back into your FAT table. You have to allocate a new cluster. So you have to scan the FAT table, find an empty cluster, redo the entries in the FAT table so that they have a new one in the chain. Then you have to go back to the cluster, into the new cluster, write your 5 blocks, and then return. But of course, you have to do that in a big loop. So you either have to do it, you have to keep doing that until the data is done, or until your file block is full, allocate a new block, and then go again, and you just keep going until the data to write is empty. Which is that's non-trivial to do, right? That is the bulk though of what the logic we have to do is. So if we go to append file, you'll see here we've got write data to the last cluster. So under the hood there, that'll go off, it'll find the last cluster, it'll write data to it, it'll return some data, which is like the data that's left to be written, or empty data. It'll return you how many bytes were written. You can update the file size in the interim here. Then you have to check and see if there's data left to be written. If there is, then you have to get the last cluster. You have to allocate the next free cluster. And then this keeps running in a loop until the data is gone. Then at the very end, you have to update the file size, which is on the disk. So there's the special file entries that exist. This is where things do start to get a bit mad to think through. So the actual file entries that tell you what files are on the disk, they have a file size in them. And that file size is really important for reading back the data from the disk, because I don't know if I touched on this before, but the clusters in a disk are somewhat reusable. And so when you delete a file from a disk, you don't actually clear out the clusters mostly. You basically just leave them. But you destroy the pointer that tells you that this is the data. But the data is actually still written on the disk. So there's stuff you'll do to secure it. That's why people say, oh, if you just delete a file from a computer, that doesn't mean it's gone. And it doesn't necessarily mean it's safe, that you assume that the data is all just gone. What you have to do is you basically have to go through the entire disk, and you have to like zero out every byte in the disk if you actually want to clear it completely and make sure it's all safe. So that means that for any cluster that you're reading that's part of a file, there could be junk data in that cluster. So how do you know that you're actually reading your file's data and not just junk data? So if you just read an entire cluster that you know is part of your file, so typically this will be for the last cluster of the file. So if you read, like, if it's 512 bytes, you read 128 bytes, so if you keep reading the rest of that data, there could be actual data in there that isn't associated with your file. And you can't just return that because it's not part of the file. So what you have to do is you have to know when to stop. And the way you know when to stop is because you know how big the file is. So you know how many bytes to read. And then at that point, you just stop reading. And then the rest of what's in that cluster could be anything. It doesn't matter. So that's just a subtlety with this, that you have to then, after you've appended the data to the cluster, you then have to go and you have to update the original file record to reflect that. So if we go into this one, then this goes off and see it's doing stuff with the with the file entries, and it's going to basically overwrite some of the data on the disk, which represents the file size. What else? That's appending to file. Creating file then logically is not much different, I suppose. Well, I suppose it is in a way. You have to do things with allocation of clusters. So the first thing you need to do is you need to find the first free cluster on the disk, and you want to allocate that. At this point, because there's nothing in the disk, you're only allocating one cluster, which is its first and last cluster. So you're going to allocate a free cluster. I'm not going to get into what this is. This is a little bit of implementation details, kind of a hack that I had to do to make it work, but let's forget about it for now. You need to create your file record. So this is, I have passed in the name. Excuse me. And then, we generate the file itself. And then we're going to append to a file. The file we're appending to here isn't the new file. It's actually the root directory file entry. As remember, in FAT32, unlike FAT16, the root directory is actually a file in and of itself, or well, any directory is a file in and of itself that has entries in it. In this case, the root directory is always like a static location. It's basically the first location in the first cluster available on the disk. So we get this. I have this. It's called the fake file record because I don't have an actual file record for it. There's a weird nuance in there with the file size as well, because you can't actually know the file size for the root directory. It doesn't work the same way as other files work. So you have to either derive it or just kind of make up a number for it. But I need to append to that because that entries on that disk tell you what files exist. So I allocate the cluster for the file. I create the fake file record with the cluster, and then I append it to the root directory cluster. And then at that point, you can ignore what this does. Again, it's some strange nuancy stuff that isn't super important, but we return the new file that's written, and then that's it. We can then use that file as we can any other file, and we can write to it, etc. So that's about it. Maybe I'll show you guys this actually running. So I have a few helpers up here, so I can create files, can append a file, print the files, but this one is probably the most useful one, which is it's a load test that I wrote. So basically this just creates 100 files on disk and writes basically a random string that is 6,500 bytes long, does that 10 times one line basically each, so it's big long lines of data, appends them into it, and then this just does a few things. It just reads from the disk, checks the size that it's written, and counts how many files are written. But then I can open up my Finder. If I use a real file, I can open up my Finder and I can show you guys the actual files that were written to the disk. And this is a use case that basically mimics what I'm going to be doing with this in real life. So let's run it and see what we get. First thing I have to do is I have to unmount the disk. So I have it here. It's dev disk 4. I need to unmount it. from my file system so that I can write to it. That's fine, that's done. So then what we're going to do is we're going to go uv run slash examples slash dot slash examples slash what's it called, load test.py, and then dash dash path equals slash dev slash disk 4. Okay, so this should work now. This should access my, so it should run this load test script. It'll run it against dev disk 4, which is an 8 gigabyte SD card that's plugged into my computer right now. So if I hit enter here, it's going to take a few seconds to do it. And there it goes. So it wrote this many bytes to this many files. This is actually incorrect. It should have only written 100 files, and it actually did only write 100 files, but there are 5 junk files on that disk already, and it's actually just the code that's in here specifically has managed to read those out as it scanned the disk for the files that were on it. So you can ignore that. I just hadn't formatted the disk between some previous junk testing I was doing before. But let's have a look then at our Finder, and there's my disk logger. So if I click on this, there we go. I have a bunch of files. So test 0, test 1, test 2, all the way up to test 99. And these are just those junk data files. If I click on one, you see it's got 65 kilobytes, which is what we'd expect because we wrote 10 lines of 6,500 bytes each, which is approximately 65 kilobytes, not including the little character that's in there too. And these are all the same. They will contain different content, but they're the same size, same number of bytes written to them. So if we have a look at one of those, drag it over here, there we go. There's just a bunch of random data, but you can see there's new lines between each one, and there's 10 lines written to each disk. So this is somewhat relevant to what I will actually do with this in real life, and that is what I will plan to do with this is that it'll be basically for logging data out, like literal log files, or logging data out, just like data files. So what you're likely to have is you're going to be creating a file maybe once at the very start of the boot of the device, and then you're just going to be appending lines to it one after the other. And that's all it'll ever do. You'll never delete those lines. You never modify the file from the start or anything. You'll always just append to the bottom, which is like how a log file works. So that's basically what we have done. So there we have it. That's our feature. That's our thing built. It works. It does its thing. Not the most exciting thing in the world, but it took me a long time to get to this point. I never thought I'd be so excited just to be able to append data to a file. But this is done all at the very lowest level, basically, which is pretty cool. So next step for this is this functionally is complete. All the Python code, I'm not going to do any more Python for this. So this code is basically done now. I'm going to leave it as it is. Next step is to start writing the Rust code for it. So I'm going to pretty much clone this and just do it in Rust. I'll try and make it run the same kind of way so that I have some example code and I can run it, run unit tests to test it. I can also run it against a disk on my computer locally and have it all work. The only real stipulation is that I want to write it as no std Rust so that I can run it on an embedded system, basically. So yeah, it'll be pretty low level, very simple stuff, nothing fancy or complicated. But the thing is, because I've already broken the back of how the logic works and how I want it to work, and I know I can do this, I know I just have to basically re-implement it in Rust. I've already done all the thinking. It's just more now having to translate it into Rust and also maybe shift how I do a few things to make it more idiomatic in Rust. And also, I'm not sure if there's definitely parts in here where I use some nice Python stuff that doesn't exist in Rust, so I'll have to correct for that as well. But yeah, that's it. That's where we're at too. So I was hoping this video would be short. I can't seem to ever make a short video when I'm talking about this stuff. I'm sorry, I just tend to go on a bit. But yeah, we're going to leave this here. Next steps, if you want to come back later, we'll be talking through the Rust implementation of this. No idea how long that's going to take me to do. Probably a few weeks, but anyway. I'll come back with that, and that'll be the next video. So let's leave this here for now. If you've watched along with me this whole time, thank you very much, and fair play to you. This is not exactly the easiest ramblings to follow, but I hope this is at least interesting to someone. I hope someone gets something from this or inspires them to go off and maybe learn some super low-level thing that they just never had really thought about before. I know I really love when I actually do that. Not necessarily always the most practical thing to do, but I always get a huge amount from doing it, and I really, really enjoy it. So, as always, thanks for watching, guys, and I will see you in the next one. Bye-bye.